Okay, so this is actually even serves as a review, right? Because there's not too much else. Well, there's a few things, but not too much else to talk about. So first, like we did in class, classify each number as rational or irrational. If rational, determine if it's also natural, whole, and or integer. All right, so square root of 81. That's easy. It's a perfect square, so that's just a 9. And 9 is a natural, right? It's a whole number as well. It's an integer, and obviously also rational. I need a calculator. And we're doing the square root of 222. Well, square root of 22 is not the perfect square. If you look through your list, you won't see it. So square root of 22, if you put in your calculator, it's going to get 14.89966443. And because we know it's not a perfect square, we know it's going to be a decimal that goes on forever and ever. Doesn't repeat, irrational. 2.8793, and then remember our definition of rational number. If I can express it as a ratio of two integers, it's rational. So can I change that to a fraction? Can you? You can. What's the place value of the 3? 10, 100, 1,000. So it's 10,000. And 287,983. So because I can write this as a ratio of two integers, it is a rational number. And I can simplify it, but I don't want to. You guys can figure that out. 2.347347. It's a repeating decimal. And repeating decimal, remember, we can go through this process. X equals 2.347, multiply the top and bottom by 1,000, etc. Right? We can go through that process and change this to a fraction, right? We can actually write that as a fraction. Therefore, this is rational. So any number, if I can write it as a ratio of two integers, also known as a fraction, it's a rational number, right? 94 point, all these numbers, ... looks like a decimal that goes forever. Does it repeat? No, it doesn't, so that makes it irrational. 5 plus square root of 100, well, square root of 100 just means 10, which is now 15. So this is, again, natural, a whole number, an integer, and obviously a rational. Square root of 36 is just another way of saying 6. Square root of 64 is just another way of saying 8. That gives me 14. So again, it's a natural number, it's a counting number. Sorry, natural counting. It's a whole number, it's an integer, and obviously rational. Well, this is 3 times the square root of 19. Let me find out what square root of 19 is. Square root of 19 in the calculator would give you 4.35889894. ... Again, not a perfect square, so we know it's going to be a non-repeating, non-terminating decimal. And it says here times 3. So imagining getting this number that doesn't end, it goes on forever, and multiply by 3. Well, it's still going to give me a decimal that goes on forever, right? ... So this eventually becomes irrational, right? Because the ending result, it's still a decimal that doesn't repeat and goes on forever, just multiplied by 3. All right, so that was easy. What kind of decimals are irrational? Well, non-repeating, ones that don't repeat, and non-terminating. Terminating, which means they go on forever. So it doesn't repeat, it goes on forever. Why? Because I cannot write that. Why? Because I cannot write it as a fraction. Okay? Keep saying that, but the better answer is because I can't write it as a ratio of two integers, but that's okay. What decimals are rational? Terminating decimals and repeating decimals, right? Because, again, that's a terminating decimal. 2.5, 0.9. Can I write these as fractions? Yeah, I can. 2.5 would be 25 over 10. 0.9 would be 9 over 10. So can I make this change? I can. Repeating decimals, 0.3333, blah, 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 forever and ever. Can I change that to a fraction? Yes, right? We know the method now, so that would be 1/3, right? So because we know how to change a terminating, right? We proved that we can change a terminating decimal to a fraction. We can also write a repeating decimal to a fraction. And remember, if we can write it as a fraction or as a ratio of two integers, guess what? They're rational. Change the decimals and simplify. Well, the 5 is in the hundreds place, so let's write 325. Can we simplify that? That would be 3 and... So if you simplify, that would be 3 and 1/4, right? 0.234 is 234 over what place value? The thousands. Can we simplify that? We can. 234 over 1,000. That's simplified would be 117 over 500. 0.8 would be 8 over 10, or simplify 4 over 5. 4.08 would be 4 and 8 over 100, or 4 over 2 over 25. Okay, so again, the point is, can you take a decimal, a terminating decimal, and express this as a fraction, first of all? Yes. And if I can, it makes all these decimals, terminating decimals, rational numbers, right? So any fraction that terminates, we can express it as a ratio of two integers. Repeating. Well, let's go through the process. So x equals 0.747474 dot dot dot. There's two repeating numbers, so I'm going to multiply the left side and the right side by 100, so times 100. Take this side and multiply that by 100. So 100 times x, that's the easy one, x 100x. And then take that and multiply it by 100 in your calculator. You'll see that it's going to give you 74.747474 dot dot dot. Now we can subtract. Notice that for all these repeating, the repeating side of the decimal will be 0. And then 100x minus x is 99x. 74 minus 0 is 74. Divide by 99. Divide by 99. Right? This simplifies to 1. X equals, excuse me, 74 over 99. And you can double check. Here, again, same thing. X equals 1.42525, because that's the repeating part in this question, right? So I want you to... Now, two digits are repeating, so we're going to multiply again by 100, right? The repeating numbers, the number of repeating numbers, we determine what power of 10 we multiply that. So one repeating number times 10, two repeating numbers times 100, and so forth. So 100 times x, that's the easy part, right? 100x. Now, multiplying by 100, right, the shortcut, if you don't want to put it in your calculator, is just move the decimal twice to the right. So if you move, so here's my number. I'm going to put it right here, 1.425252525. If you move the decimal 2 over, it's going to become 142.5252525. So let's write that down. Let me just push this guy a little bit to the side. So multiplied by 100, right? Our original equation was like this, x equals. And then this was 100x. Now we're going to multiply, make that way too big. It was x, and then we multiply by 100, we get 100x. And then we multiply this by 100, and we get 1.142252525. Remember, the reason we're doing this is because we want to get rid of the repeating part, right? So we line up your decimals correctly, right? So you're subtracting the correct place values from each other. So decimal comes down, dot, 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 dot. This goes away. 2 minus 2 is 0. 5 minus 5 is 0. 2 minus 2 is 0. 0. 2 minus 2 is 0. 5 minus 5 is 0. 2 minus 2 is 0. And when you get to this, it's 5 minus 4, which is 1. And then 142 minus 1 is 141. Let me just write that a little better. So on the right side, if you subtract, you get 141.1 equals 100x minus 99. Minus x is 99x. Sorry. Divide this by 99. Divide this by 99. X equals 141. 141.1 over 99. We could clean that up a little bit better, but let me just confirm. 140. Let me put that as a fraction. 141.1 divided by 99. Enter 1.425252525. So we are correct. So if you got this far, I'll take it. We could clean that up a little bit so that we don't have any decimals. Okay, we can multiply top and bottom by 10. If you did that, you would actually get 1411 over 919, and you wouldn't have that decimal, right? So I multiply this by 10, this by 10, just so that I don't have decimals in the numerator. And anyways, if you got this far, you'd be okay. Determine if the fraction is terminating decimal or a repeating decimal. Remember, we're looking at the denominator. That's where he holds the key. Look at 22. So look at the denominator, 22, and let's rewrite 22 as a product of its prime number. So forget the numerator. So focus on 22. So if I had 22 and broke it up, that would be 2 and 11. Right? So 22 is the same thing as 2 times 11. But remember what we said in class. If the denominator can be written only with 2's, or only with 5's, or 2's and 5's, then it's terminating. Anything else, if it includes 11, 3, 7, all those numbers, anything but 2's or but 5's or but 2's and 5's is it's terminating. But 2's and 5 is repeating. So this repeating, right? Because 22 can be written as a product of 2 times 11, and again, anytime you have a number different than 2 or 5's or 2's and 5 is going to be repeating. 8 over 19, well, also repeating. If you take the number 19 and you break it up, you get, it's just 19, right? So this is repeating. So and again, take the calculator, 8 divided by 19, it's going to be a repeating number, okay? 2 over 22 is a repeating number. 1 over 200, well, let's break up 200. 200 is 2 and 100. 100 is 2 and 50. 50 is 2 and 25. And 25 is 5 and 5. So if you broke up 200 into its product of prime numbers, look, it's made up of 2's and 5's. So if you made up of 2's and 5's, this is not repeating, this is terminating. Right? As long as it's all made up of 2's, or only 2's and 5's, or just 5's. So if you take a calculator and divide 1 by 200, you get this nice pretty decimal, 0.005. 7 over 50, take the 50, break it up. 50 becomes 2 and 25. 25 can be broken up into 5. So 50 is 2 times 5 times 5, which again is made up of just 2's and 5's. So this is terminating. It's not going to be a repeating decimal. Again, 7 divided by 50, you get 0.14. 64. Ooh, let's break up 64 into 8 and 8. 8 becomes 2 and 4, and then 4 becomes 2 and 2. You break, right, until you can't anymore. So 64 is the same thing as 2 times 2 times 2 times 2 times 2 times 2. So it's all 2's, right? So writing 64 only using prime numbers is 2 times 2 times 2 times 2 times 2 times 2. Notice that they're all 2's. So 64 is just 6 2's being multiplied. So because it's just made up of 2's, it's also terminating. And then if you do 33 divided by 64, you'll see that in your calculator you get 0.515625. 9 over 62. Well, 62, I'm going to tell you, is 2 and 31. And 31 can't be broken anymore. So 62, right, the denominator can be written as the product of 2 times 31. And guess what? Because it's not only 2's, not only 5's, or not only 2's and 5's, it has a different number, right? 31, this is going to be repeating. Right, so remember, if it's going to be terminating, it has to be made up of 2's or 5 or 2 and 5. Once it has any other different number, you know it's going to be repeating. And then 9 divided by 62 equals to 0.14516,129. And I wish I had a bigger calculator. Let me see if I can pull it up. Calculator with 100 digits. Let's see if we can do that. Full precision calculator. All right. So let's do 9 divided by 62. Oops. 9 divided by 62. Let's see if that gives us a better see. 0.15146. Let's see where the repeating part is. Right, 4, 5. You see here? It's 451629, 451629. So it's a repeating decimal. We just don't see it in the calculator because we don't have any digits, but it does repeat. Okay, so actually that was a good one. Okay. On the next page, approximate the square root of 299. All right, so let's do the double number line first. Square root of 299 is between, let's see, 16 times 16 is 256, okay? 17 times 17 is 289, so definitely it's between 289, which is the same thing as 17. And then 18 times 18 is 324. So the square root of 29 is somewhere between those two numbers. And square root of 289 is just known as 17, square root of 324 is 18. So 299 would be somewhere there. Let's see, 289, 90, 95. So let's make that 90, 95, 300, 305, 310, 315. Let me make it just a little bit bigger. 90, 95, 200, 205, 305, sorry, 310, 315, 320, okay. 389, 90, 95, so square root of 299 somewhere over here. And if I drop that, what does that look like? I don't know, 17.3, maybe 17.3, so, right? So let's leave that at that. Now let's do this one on the other side. 299, and we know that it's the biggest perfect square that goes in there is 17. So let me just add the zeros here. 17 times 17 is 289. We're going to subtract. We got 10 left over. Let's bring these two zeros down. Next step, double 17. We get 34, and add a place value here. So it's about 340 something. So I'm going to say it's only 2 times because 343 times 3 equals, that's 10,000, 1,020. That's too much. So remember, this number and this number has to be the same. So if I put a 2 here, I must put a 2 here. 342 times 2 equals 684 minus we get 316. Bring these two zeros now. Remember, we double the top. 172 times 2. It's going to be 344. Add a place value. So this is 31,000. This is about 3,500. 7 times. 3447 times 7. Let's try 8. 3448 times 8. Really? 3449 times 9. 9. It works. Wow, really? So now, if that's a 9, remember this is going to be a 9 as well. So let's multiply 3449 times 9 gives you 31,041. And if you subtract, you get 559. Bring those two zeros down. Let me change colors. So now we're going to double the top. 1729 times 2. We're going to double. You get 3458. Place value over here. So again, let's think about this. This is about 35,000. This is about 55,900. So it looks like a 1, right? That makes sense. 34,581. Subtract 10 minus 1 is 9. 9 minus 8 is 1. 8 minus 5 is 3. There. So let's take the square root of 299, my calculator. And notice that it's going to be 17.291. The first 3 decimal places is exactly what we got. Good. Next one, square root of 29. All right, so we'll do it both methods. Well, it's between the square root of 25 and what's the next one? 36. That I know for sure. 25, 26, 27, 28, 29, 30. 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. Good. 26, 27, 28. So square root of 29 is here. Square root of 25 is 5. Square root of 36 is 6. So let's drop a line. So that looks like 5.3. I'm going to say 5.3. Right? So using this method, we get about 5.3. Let's do the other method. We're going to write 29. Let's add zeros. Don't forget a decimal. Biggest square, perfect square that goes to 29 is 25. So we're going to write 5 and 5 here. That gives us 25. Subtract, we get 4. Bring 2 0 down. Change colors. Double 5, we get 10. Put a place value there that we're going to fill in. So 100 and something goes into 400 how many times? So it's obviously 3 times. So we're going to put a 3. That's going to give us 309. Let's subtract. We're going to get 91. And then the 2 zeros come down. These 2 zeros come down. Double the top. 53 times 2 is 106. Place value over here. Change colors. So that's about 1,000 and change. I'm going to say 1,067 times 7. Yeah, try 1,068 times 8. Right, 8 times it is. So if I put an 8 there, remember 8 goes here, and that gives me 8,544. 10 minus 4 is 6. 9 minus 4 is 5. 10 minus 5 is 5. 556. Bring the last set of 0 down. Let me change colors. So we double the top. 538 times 2 doubled is 1,076. The place value there. Now we're going to have to figure out. So that's about 11,000. This is about 55,000. So maybe 5 times. So let's put a 5 here and a 5 here. Let's see if that works. So 10,765 times 5. Sorry. 10765 times 5. 53,000. Yeah, 5 seems the correct number. So it's 53,825. And we subtract, we get 1,775. Well, we're only going to 3 decimal places. Let's take the square root of 29. And in our calculator, it says 5.385164, blah, blah, blah. But notice that the first 3 decimal places is what we want. Okay, so I wrote this incorrectly. Okay, so I wrote this incorrectly. I don't know why I wrote it like that. This, hopefully you'll fix it, should be c squared equals 900. All right, so how do we solve that? Well, we're going to take the square root of this side and the square root of that side. There's an invisible 2 there that allows us to cross those 2 and allows my c squared to become c. Square root of 900 now, right, in this format when we're looking for. So look at the question we're looking at, and we're looking for a number that we can take to a second power that gives you 900. So the answer is plus 30 and minus 30. Oops, plus or minus 30. Let's do a check. If I use positive 30 and take it to second power, does that equal 900? Well, 30 times 30 times 30 is 900. And that works out. What if I take negative 30 to the second power? Would that give me 900? Well, negative times a negative is positive, and 30 times 30 is 900. So that also works. So for this equation, positive 30 and minus 30 can be plugged in here and give me 900. Again, please rewrite the question because it should be written like this. So please don't pay attention to that. Again, how do I get that equation to look like this? K alone by itself without the exponent of 2. Well, you're going to take the square root of this side, and you're going to take the square root of that side. There's an invisible 2 here that crosses out, leaving k by itself. And square root 361 is 19, but remember in this case, plus or minus 19, right? Because positive 19 will work and negative 19 will work. Let's do a check. So if we use positive 19, it's going to be 19 squared equals 361. 19 squared is 19 times 19, which is 361, and it equals 361 on that side. What if I use negative 19? Well, negative 19 to the second power equals 361. Negative 19 times negative 19. Negative times a negative is a positive, and 19 times 19 is 361, which equals to 361 on that side. In this question, the answer to my problem is plus or minus 19. This one is, I'm not sure I like this question right now, but something to think about. Is an irrational number plus another irrational number always, never, or sometimes irrational? Give examples in your situation. Well, let me go back here. And allow me to use this problem here. So, how do I do this? Here's pi. Okay, good. So again, we know that pi goes on forever and ever and ever and ever. So I'm just going to take up to here. Copy. Let me go back. This. No. Back to this. Okay, here we go. All right. Let's use pi as our example. All right. So again, we know it goes on forever. So what happens if I put this under and I add dot, 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 dot. Well, let's think about that. Right, plus, right? Now notice that it goes on forever and ever, so I would add this and this, this and this, this and this, this and this, this and add, right? Keep adding, keep adding, keep adding, and then 4 plus 4 will be 8, 8 plus 8 is 16, carry 1, and so forth. Will it still give me a decimal that goes on forever and never and doesn't repeat? Yes. So in this case, an irrational number plus another irrational number makes sense, right? It still gives me irrational, right? Because pi never ends, so the top line is a number that never ends. The second line number is a decimal that never ends, goes on forever, right? And if I add both of them, one to each other, I still get another number, another decimal that goes on forever and ever, and then repeats. I hope everybody is okay. So in this case, it would be always. But can you think of a case where irrational plus another irrational gives me a rational? How would that happen? Well, what if I did what if I did pi plus negative pi? What would I get? Think about that for a second. Pi plus negative pi. Wouldn't I get 0? And what's 0? 0 is a rational number, right? Remember, 0 belongs to the whole numbers, to the integers, right? So 0 is on this category. So there's an exception to this. So square root of 2, it's an irrational number. It's a decimal that goes on forever and ever and never repeats. Plus negative square root of 2. We're adding a rational number plus another rational, we're now adding an irrational number plus another irrational number. And that gives you a rational number. It's kind of silly, but something that for you to consider, right? So the only exception here, that I can think of, exception of when an irrational plus another irrational equals to a rational is when you add 0 pairs. Think about that. Oh, additive inverse. 5 plus what equals 0? Well, it would be negative 5. 100, negative 100, 1003 plus what equals 0? Well, that would be 1003. Well, the opposite, right? So even with irrational, so if you took a number like square root of 2 that we know is a decimal that goes on forever, never, and doesn't repeat, so therefore is irrational. But to that, we add its opposite. It gives us a rational number. Right? Something to consider. Let's see. Yeah, well, that's it. So if you had pi and you add another pi, right, that gives you irrational. But if you take pi and you add its opposite, guess what? It gives you 0, which is rational. All right, that's it.